Thanks very much for the invitation, David, and of course I already mentioned how grateful I am to him and to all of you for coming. And what I want to tell you about today is a project that's been going on in my lab since I started at Tufts about 3.5 years ago, which is the design and synthesis and testing of materials that show a response in terms of their photoluminescence to the reactive oxygen species Singlet-Oxygen. And so we do a number of things in my lab as just a brief introduction. What we generally focus on is integrating known photochemical reactions into organic molecules to give those organic materials new photoresponsive properties. And so what I'm going to be focusing on today is sort of the bottom half of this slide, which is new materials that show, like I said, a photoluminescent response both in solution here and in the solid state to Singlet-Oxygen. And so as a brief outline, I'll give you just a brief introduction to some of the selected properties of Singlet-Oxygen that I, as an organic chemist, think are particularly interesting, and then a brief overview of conjugated polymers as fluorophores, basically. Then there's two sort of sub-projects I'll talk about, which is Furan-substituted conjugated polymers that show a quenching of photoluminescence in response to Singlet-Oxygen, and also acene-substituted materials that show a ratiometric response in photoluminescence in response to Singlet-Oxygen. We also have gotten this to work in the solid state and in aqueous environments. And finally, we've been able to engineer some reversibility into this response through some molecular design. So just as a brief introduction to Singlet-Oxygen, Singlet-Oxygen is an electronically excited state of ground state triplet oxygen. So ground state triplet oxygen electronic configuration is here on the left. There are actually two different ways you can write the electron configuration of Singlet-Oxygen. The one I'll be talking about is the lower of the two energy states here, where the electrons are paired in the same orbital. And so when I say Singlet-Oxygen, what I'm talking about is oxygen in this electronic configuration. Now, as an organic chemist looking at Singlet-Oxygen, why would someone like me be interested in it? Well, from an organic chemistry perspective, Singlet-Oxygen does beautiful organic chemistry. It does things like ene reactions with alkenes, and it deals Alder-type Cycloaddition reactions with these molecules, these polycyclic acenes, namely anthracene or tetracene or penacene. And it actually does this reaction in a very clean fashion and does so with pretty impressive rate constants. It turns out that the rate constant between Singlet-Oxygen and penacene is somewhere around 10 to the 9 inverse molar inverse second. So we're approaching diffusion control here for a very clean reaction. It turns out that there's a number of people in the sort of organic semiconductor field that want to, say, take penacene and make really good transistors out of it or other types of devices out of it. And this reaction is actually a real problem for people who want to use penacene to do that because it's so efficient that you can see here this is a solubilized form of penacene in organic solution. If you go to lunch and leave it exposed to light and oxygen for a little while, it's totally bleached by self-sensitization through this cycloaddition reaction. Someone like me looks at this and says, clean reaction, really fast, and dramatically changes the optical properties of this molecule is something that we think is pretty exciting to use. And so another thing that we really like about Singlet-Oxygen is the fact that it's chemically amplified, that is, with respect to a sensitizer. That is, you can take a sensitizing molecule like this dye, this is methylene blue, and you can do this with a number of different materials or molecules. And upon excitation to a triplet state after intersystem crossing, you get something like a triplet-triplet annihilation energy transfer event, where you basically come back and regenerate the sensitizer in its ground state and produce a molecule of Singlet-Oxygen. And so here the stoichiometric reagents are light and O2, and we can recycle the sensitizer many times. And this is useful in a number of applications, of course, both from a synthetic perspective, so synthesizing things like endoperoxide and products derived thereof, and also in things like photodynamic therapy, where the reactive oxygen species are used for their cytotoxic capabilities. So that's all I wanted to say about Singlet-Oxygen generally, and let me just sort of give you a brief introduction to conjugated materials. And conjugated polymers are organic macromolecules that we prepare synthetically, but unlike their sort of more common brethren like polystyrene or PMMA, which have electrically insulating backbones or non-conjugated backbones, conjugated materials share the feature that along their main chain you have pi conjugation between monomers. And so you can see here that with the PPEs, the polyphenylethylines or polyperols or any of these general classes, what we see is that same structural feature of pi conjugation along the main chain. As such, they have properties that sort of make them like organic semiconductors, and having those properties means that they exhibit a number of useful optical properties or electronic properties or optoelectronic properties. A number of sort of things are useful there. But because we prepare them with the sort of techniques and design features of organic chemistry, that allows us to access a wide variety of structural motifs that we can generally put together with sort of plug-and-play like modular synthetic techniques, particularly the organometallic cross-coupling reactions. Now, applications of these have been numerous, including photovoltaics and light-emitting devices, and in addition to chemical and biological sensors. And one of the reasons that some people are interested, like myself, in using these materials in sensing applications or responsive applications is the fact that you can get sort of a unique form of amplification that derives from light harvesting. And so if you think of having a small molecule fluorophore that has a highest occupied molecular orbital and a lowest unoccupied molecular orbital, and then some molecule way over here that you want this excited state to interact with. Well, if there's a significant distance between that exciton, that excited state, and that molecule you want it to sort of to look at, then you're not going to have any sort of communication between those two systems. With organic semiconductors, what we're able to do is sort of put a little bit of a highway for that exciton in here, and this can either be an exciton, as I'm showing here, or a hole, or an electron charge carrier, so that we can get sort of movement or migration of that exciton such that it might arrive close enough to our trap, our molecule we're interested in looking at, such that we get some event, say an electron transfer event or an energy transfer event, or something that we can transduce using, say, photoluminescence. And so this is one of the reasons why using these sort of semiconducting materials is interesting. And so what I'm going to do here is tell you about a project that was actually just completed, we actually just published recently, where we use furan derivatives, and furan derivatives undergo cycloaddition reactions with singlet-oxygen to form this intermediate endoperoxide. And now the furans that we're starting with are relatively electron-rich. They don't really want to accept electrons very readily. And so that unoccupied orbital of the furan is pretty high in energy up here, significantly higher than the excited state electron of our fluorophore. Upon cycloaddition with singlet-oxygen and subsequent reactions, this endoperoxide is not stable at room temperature, we form these oxidized products that are now much more electron poor. And being electron poor, they can more readily accept electrons by being reduced. And so what we've done is we've now taken that furan orbital, that unoccupied orbital, and decreased its energy, such that, at least this was the hypothesis, that we could then get an electron transfer event and see a diminution in fluorescence intensity upon exposure of this type of material to singlet-oxygen. So that was the general hypothesis that we had going forward. And so we do a lot of organic synthesis in my lab. I'm not going to belabor this, but basically the design of this is that we have our fluorophore here is a conjugated backbone of this polymer. We made a number of these furan derivatives. And the singlet-oxygen responsive moiety is this diaryl furan here. And so there's the number of sort of derivatives that we made. And what I want to sort of first call your attention to, and something as sort of physical organic chemists we always want to pay attention to, is can we understand how the structure of this reactive moiety, this thing that we're going to actually get to respond to singlet-oxygen chemically, how does it react in a way that we think is understandable from a structure-property relationship standpoint? And so that's exactly what we do. So while we're sort of worrying about the luminescence properties, and I'll get to that in a slide or two, we always study the kinetics and the physical organic chemistry of these compounds to make sure they make sense. And so what you're looking at here is the rate, the pseudo-first-order rate of these compounds, and here what I'm showing you is the different substituents that we put on this diaryl furan. And we look at the rate of disappearance of it upon exposure to singlet-oxygen as a function of structure. And as you see, as you might expect, as we make this furan more electron poor by putting on electronegative fluorine atoms, we decrease the rate of cycloaddition significantly. All of these reactions follow pseudo-first-order rate laws because we're keeping the concentration of singlet-oxygen at a steady state under these photosensitization conditions. Moreover, something that we worry about greatly when using organics and exposing them to reactive oxygen species like singlet-oxygen is degradation of chromophores that we necessarily don't want to degrade. And so this is something we're always cognizant of and taking a look out for. And so what you're looking at here in the upper right is the UV spectra of this diaryl furan as a function of time upon exposure to single oxygen. You see a relatively nice isospecistic point and nice disappearance of oxygen and appearance of oxidized products. Now what we're looking at here in the bottom right is the UV spectra of the polymer, this conjugated polymer which is going to be our fluorophore, with a furan attached. And you can see south of about 360 nanometers, we see the same sort of response of the furan moiety to singlet oxygen here. North of about 370 nanometers, where only the polymer backbone absorbs, we see no degradation of absorbance, which is really important for us, especially since we're looking at a fluorescence quenching event. And so the conjugated backbone here is stable under our reaction conditions. So in terms of fluorescence, what do we observe? Well, we observe, just as we predicted, we observe a rapid fluorescence quenching of this donor fluorophore of this conjugated polymer. So upon exposure to singlet oxygen, what we observe is a relatively rapid response that corresponds to the reaction between singlet oxygen and this furan moiety. We see down to about 75%, so a threefold decrease in fluorescence intensity upon reaction of all the furan groups. When we make the donor fluorophore, or the electron donating fluorophore, a smaller band gap material, we decrease the energy of that excited state electron, even though the furan undergoes a reaction with singlet oxygen, an analogous reaction as we see up here, and we can confirm that with both UV and NMR evidence. We see no response in terms of fluorescence, which means that the energy of the excited state is a really important consideration when talking about electron transfer here. Now, 75% is fine. We wanted to see if we could improve this a little bit, and we did so by sort of designing a polymer that made these furans both better oxidative quenchers by making them more electron poor, and also doubling up. That is, we sort of put twice as many potential quenchers per monomer unit as we did over here. And under these circumstances, although the response is somewhat slower, we see over 90% fluorescence quenching upon reaction of all the furan derivatives. This was published just recently this year. Now, this is all I'm going to say about the furan derivatives because, frankly, this has a number of disadvantages. One, all of the reactions I've showed you so far have been an organic solvent, and so that's of limited utility. Another thing that's of limited utility generally is fluorescence quenching a sort of response because of the problems associated with adventitious quenchers or photo bleaching or things like that. And so fundamentally this works the way that we predicted, but from an applied standpoint it has limited utility. And so what we've also been looking at, in addition to the furan derivatives, are acene derivatives, and these are molecules that have these fused benzene rings like this. So this is an example of a tetracene because it has 1, 2, 3, 4 fused benzene rings together. And again, I won't belabor the point of the synthetic chemistry, although that is what we spend a lot of our time doing, and just sort of focus on the chemical structures of the materials that show this response to singlet oxygen. And two examples are shown down here. I'm actually going to focus on this one on the right here. But basically what they comprise is the same sort of conjugated backbone I showed before, the so-called polyfluorine cophenylene backbone, which is sort of highlighted in purple because it emits sort of in the violet area of the electromagnetic spectrum. And then we have tethered to it via an electrically insulating linker, either an anthracene or a tetracene moiety, each of which can react with singlet oxygen via the cycloaddition chemistry I showed early on in the talk. So again, just like we do with the furan derivatives, we always want to make sure we understand the reactivity in the products of the reaction between singlet oxygen and our acene units here. And so again, pseudo first order rate law kinetics of both our anthracene derivative pendant and our tetracene derivative pendant show that we see pseudo first order kinetics, and as well as a 20-fold increase in rate for the longer acene, which is certainly one thing that you would predict based both on the sort of the known chemistry of these acenes. We see a 20-fold increase in pseudo first order rate for our tetracene versus our anthracene, which is one reason we focused on the tetracene substituted polymers. They show a much more rapid response. Okay, so what does the polymer do in comparison to the furan derivatives I showed you before? Well, what I'm showing you here are in dichloromethane, again in a halogenated organic solvent, the optical properties of this acene here that are in dotted lines, And so you can see that we see for this acene, we see the characteristic signals for a tetracene. That is, we see this very sharp signal in the UV and this characteristic vibronic pattern in the visible region of the spectrum. And we also see a very sharp and well-behaved fluorescence spectrum in the green region of the spectrum. In terms of the conjugated polymer, we see that we also have the tetracene units appended to it, and as well we see this very characteristic broad signal between about 300 and 400 nanometers, which corresponds to this conjugated backbone of our conjugated material here. And the nice thing is here, we can very selectively excite at 365 nanometers the conjugated polymer backbone with well under 5% of the light that we use to come in, actually going directly into the tetracene. So when we do that, we come in with 365 nanometer light and pump this chromophore here. But what we see is that the fluorescence is almost entirely coming out of the tetracene moiety. So what this is consistent with is a FRET or energy transfer process, where light comes into the polymer, transfers its energy downhill energetically to the lower excited state energy tetracene, and very efficient fluorescence coming out of the tetracene moiety. So this is setting up as compared to the furan derivative, which did electron transfer. This is doing energy transfer before exposure to singlet-oxygen. Now, what happens upon exposure to singlet-oxygen? Well, recall that the cycloaddition reaction with these tetracenes and singlet-oxygen looks something like this. It makes this bicyclic structure where we disrupt the conjugation along the long axis of the tetracene unit. And so what you see in the UV vis spectrum of a polymer that contains this tetracene is that, again, the singlet-oxygen reactive moieties diminish in intensity, but the conjugated polymer backbone again remains stable under these conditions, very important for our studies. Here what I'm just highlighting is showing this is the sensitizer that shows we can excite the sensitizer selectively and not worry about exciting the polymer. So the tetracene peaks diminish upon exposure to singlet-oxygen, but the conjugated polymer, as I mentioned, the backbone remains unchanged. It does not decompose on this time scale. Now, in terms of the fluorescence spectroscopy, what we see is something very different than what we observed with the furan-based polymers. Instead of just a quenching of fluorescence, what we see is a much more favorable ratiometric response to singlet-oxygen, where we are basically shutting down energy transfer to this tetracene moiety by breaking its conjugation, turning it into a much higher band gap pendant, and therefore making fluorescence from the conjugated polymer much more competitive. And so fluorescence intensity from the tetracene goes away. Concomitant to that is an increase in fluorescence intensity from our conjugated polymer backbone. So this is something that we thought sort of might have some legs in terms of any potential applications. Again, one thing that sort of is a disadvantage for this particular material under these conditions is, again, in a halogenated organic solvent, again, of limited utility. So then what we decided to go next is to try and see if we could move this out of organic solvent, move it into the thin film. And so these polymers that we make are very, very hydrophobic, very greasy things. They're actually not soluble in water at all. It turns out they're not even soluble in most alcohols. But in the thin film, what we see is we also get a very efficient energy transfer process. So this on the left is this polymer that I just showed you in solution. And what you see is a significant amount of energy transfer such that most of our light is coming out of the tetracene. Only a small percentage comes out of the conjugated polymer backbone. But now, because this is in the condensed phase, we don't actually have to covalently link the acene and the conjugated polymer together. By putting them into a thin film, we're just dissolving or doping a small amount of this acene into this polymer, into a film of this polymer. What we see is, again, very efficient energy transfer before exposure to singlet-oxygen. And in the thin film, out in air, we see a ratiometric response in fluorescence, now not just in solution, but also in the thin film. And so that's something we thought was pretty exciting. Now, from a sort of film design standpoint, one of the things you might ask is, well, what happens as a function of, the film composition? And one thing that we thought going forward would be, well, if we decrease the amount of this dopant, then the response to singlet-oxygen should increase in rate, the fluorescence response, because there's just less of that energy acceptor to get rid of. And that's exactly what we saw. We saw much slower response to singlet-oxygen when we had very high concentration of dopant versus when we had much lower concentration of dopant. That's true both with this tetracene that we synthesize in the laboratory and also with rubrene, which is commercially available. So one thing I really like about this experiment is that this is commercially available, this is commercially available. We can make these singlet-oxygen responsive ratiometric films using only commercially available components with things you can buy from Aldrich. So one thing that we're sort of pursuing now is trying to show that we can get photochemical tuning of the emission of these thin films. And what I'm showing here is sort of a standard CIA chromaticity diagram. And this is a rubrene-doped conjugated polymer film. And using UV light under oxidizing conditions, that is, just under regular laboratory conditions out in the air, we can tune the color of the light from either the emitted light from either orange, and because orange and blue are sort of on the opposite sides of the spectrum here, we can tune through white light and go down to blue just by using one material and irradiating it with UV light under air. So this is something that we think is going to be potentially useful for making phototunable light-emitting devices. Another thing that's important about this, as I mentioned, is that this reaction is selective for oxidizing environments. That is, if we take these films and remove them from oxygen, then the reaction either slows down very severely or stops entirely. And so this is sort of a preliminary experiment we did in my laboratory where we just took a film that has some rubrene in this conjugated polymer. And what you're looking at on the y-axis here is just the ratiometric response in terms of fluorescence. And so as you go up along the y-axis, you get a more blue-shifted spectrum as opposed to a red-shifted spectrum down at the bottom part of this y-axis. So after only 10 seconds of irradiation in air for these films, we see a very rapid response in terms of ratiometric response, and we see a ratiometric ratio from 0.1 to about 0.4. Then what we do is we just in the laboratory with a couple of sort of pump down and refill cycles with argon, so not completely devoid of oxygen. After 15 minutes of irradiation under identical conditions, we see only a very slight response in ratiometric response, which we think bodes well for the possibility of this as a ratiometric sensor for O2 in environments that might be challenging. Okay, we also have shown that we can get this to respond in aqueous environments as well. And so, as I mentioned, getting things to work out in the air is one thing. Getting them to work in water would be something that would be really useful for us. And so we did a pretty simple experiment just to see if it works in water, where we just took this hydrophobic film of our conjugated polymer doped with an acene. And then we put into water a Singlet-Oxygen photosensitizer that's water soluble. We used rose bengal, but there's lots of other options. And then we selectively excited the rose bengal in water, and what you see is a ratiometric response to the photogenerated Singlet-Oxygen in water. And so that's something that, in terms of sensing Singlet-Oxygen or sensing O2 in water, something that we're just starting to pursue now. Let me skip this stuff and go right to the section where I want to discuss reversibility. Now, in my laboratory, we spent a lot of time worrying about acene design. That is, how can we make these Singlet-Oxygen reactive moieties, how can we tune their emission wavelength? How can we tune their reaction efficiency with Singlet-Oxygen? How can we tune their selectivity for Singlet-Oxygen? And so we've actually built up a small sort of family of acene molecules that we think will be useful in a number of different applications. And one application, as I mentioned before, is a phototunable light-emitting display. Now, for red emission, the obvious candidate to do red emission is penacene molecules, and penacenes are usually red emitters. But as I mentioned earlier in the talk, the penacenes are really hot. They react with a very rapid rate constant, and sort of under sort of the regular laboratory conditions that we use to fabricate films, we don't use a fab facility to do this, the small quantities of penacene required actually react so quickly that we can't generate very stable films. And so we had a challenge, which was to generate acenes that would emit red light but be a little more stable, but yet still react with Singlet-Oxygen and show this ratiometric response. So what we did is we designed a number of molecules that have this general structure, where this green portion is sort of the tetracene backbone that I've shown all the way up until now, which is a tetracene with two arene rings attached to it. And what we decided is just to extend the conjugation along this direction by simply substituting with ethynyl groups, which is a very commonly used design motif in acene chemistry. And so we designed a number of these things. And, it turns out that these did sort of what we thought they would. That is, we studied them crystallographically, and we see this really neat sort of effect that when you crowd the acene backbone actually twists quite aggressively out of planarity in the crystalline form. In terms of their fluorescence spectra, you can see that these new acenes that we generated emit significantly more efficiently than the diaryl penacenes that we initially targeted by about a factor of 3. And pretty much by a stroke of luck, have almost exactly the same emission profile as our adenosine molecules do. And so this, to us, was a success in terms of acene design. Now, one of the things that, like I mentioned early on, is when we say that these things react with single oxygen, we always need to make sure that the reaction happens the way we say it does. You see a ratiometric response, you might say, oh, it's clearly making the endoperoxide, and this is doing what we think it is. But what I always make sure that we do, or my group always does, is make sure we characterize the products of that single oxygen cycloaddition. And this is an example of one using those tetracenes that I showed earlier in the talk, where we were very easily able to separate two different regioisomeric endoperoxides, one where the endoperoxide is formed on this unsubstituted ring, and one where it's formed on this more substituted ring. And these are generally the two types of endoperoxides you'll get when you do this reaction with a tetracene. These two rings have very similar reactivities for cycloaddition reactions. And so we could easily separate these by chromatographic techniques and easily characterize them by NMR spectroscopy. So then I told my student, well, take these new acenes that you've generated, and we say they do cycloaddition with single oxygen. Well, of course, we see bleaching when we expose them to single oxygen, but we don't know what they're generating, so let's characterize the two endoperoxides. And we really weren't able to separate them by chromatography. It became very challenging, and we saw that this molecule goes away, and upon exposure to single oxygen, then upon trying to do chromatography, we see we can only isolate one of the two endoperoxides. And to sort of make the challenge even worse, we couldn't tell which one we were isolating because of the large degree of substitution on the tetracene unit. And so what we decided to do was take a look at a simpler system, and this is a molecule from the literature, this diethynyl tetracene here. And here, again, the hypothesis was that we would form two general endoperoxides. And we were trying to answer the question, why can't we separate them in our circumstance? And so if we take this and just expose it to single oxygen, here's the NMR spectrum of this molecule here. And this middle panel here, what you're looking at is showing the complete disappearance of this acene and generation of two different endoperoxides. And they are very easily characterized by these hydrogens here on the endoperoxide ring here, and these hydrogens on the ring adjacent to that endoperoxide. And we can very easily characterize them in this crude mixture. It looks like very clean chemistry. Then the student actually left the flask sort of underneath his hood in the dark for a few weeks, and it turned red. I said, well, that's great. Like, take an NMR spectrum and see what it is. And it turns out that one of the endoperoxides went away, but the other one didn't. And it turns out that this one here has a much lower barrier to reversion to this acene than this one does here. And so this endoperoxide reverts at room temperature, this one does not. And so endoperoxides generally are thought to be, many endoperoxides are kinetically stable at room temperature. It turns out that we lower the barrier for cycloreversion by making the endoperoxide here on these alkynylated positions. So what does this mean in terms of our single oxygen responsive materials? It means that we now have a way to try to make them reversibly responsive. That is, up until now, these have been sort of one-shot deals. Single oxygen reacts, you get a nice ratiometric response, it works in air, it works in water, but then the chemistry is over and the sensor is done. In these circumstances, we can actually get some reversibility out of the response. And so what I'm showing here is a preliminary experiment where we took this acene here, and the reason we use this acene is it only undergoes a single oxygen cycloaddition in this central position here. It's the only isomer that's formed. And so the only isomer that's formed has alkyne groups appended off of that position. So we doped a small amount of this into a commercially available polyfluorine and then exposed it to single oxygen and then just heated it up a little bit for a few minutes to about 50 degrees C, and we see again cycloreversion and recovery of most of the fluorescence of the acene. And we can cycle this through about 4 or 5 times. The only issue facing us right now is that the cycloreversion reaction of the endoperoxide is not 100% clean. It actually looks totally clean by NMR, but there's some insoluble products that build up. So we're looking at sort of making this into a more clean reaction and also making the cycloreversion faster to give you something that would be sort of real-time addressable to oxygen concentration. So with that, I'd like to sort of wrap up, and I'd like to, again, reiterate my gratitude to David for not only his really important and seminal contributions to all areas of chemistry and science, but also to his support for me and my junior colleagues and the department at Tufts Chemistry. Beyond that, I'd of course like to thank the people in my lab responsible for this research, the people primarily responsible in my research group for what you've seen here today. The primary person is Jingjing Zhang, pictured right here, a senior graduate student in my lab who's responsible for all of the acene work that you saw. Ezra Altanok, who's pictured right here in the front, did all of the furan-substituted materials that you saw. And Saina, a really talented undergraduate, and Damla, a postdoc who's recently moved on to Life Technologies, collaborated to do the work in thin film work in air and in water. So I thank them for their really important contributions to our group. I thank these organizations for funding. Congratulations, David, and thank you for your attention.
Any questions?
So Sam, I know you like to do a lot of the polymer engineering and really build in a lot of the functionality, but how would you compare kind of the mixing of these materials to, how efficient it would be if you actually had them integrated into the same backbone?
Yeah, so the number one problem that we face when we have them dissolved in a polymer film is phase separation. And so at high concentrations of dopant, we start to see signs of sort of macrophase separation, which of course is going to be a problem if you want efficient energy transfer. And so we really do like, from a performance perspective, having them covalently linked. But that's, of course, takes more time and energy. So, for simple experiments, we usually just rely upon the doping because it's very easy and quick to do, and we can make large quantities of films. But, for either experiments in solution, and those include experiments if we had a homogeneous system in water or an organic solvent, you really must have them linked together covalently.
Any more questions? Thank you.
Great. Thank you.